All right, let's dive in. Today, we're not just solving a mystery, we're solving the biggest mystery of all, the entire universe. And I want you to forget everything you've learned from a textbook, because we're going to treat this like the ultimate cosmic detective story. We've got clues, we've got a crime scene, a smoking gun, even a final verdict. So, let's open up the case file. You know, every great investigation starts with a question that seems almost too simple. And for us, it's this. Why is the sky dark at night? Now, for centuries, everyone just assumed the universe was infinite, that it went on forever, and had always been there. But think about that for a second. If that were true, then no matter where you looked in the night sky, your gaze would eventually land on a star, right? The whole sky should be glowing. The fact that it's, well, dark is a huge paradox called Olbers Paradox. And that was the very first clue that our most basic ideas about the universe were just plain wrong. So here's our game plan, our case file. We'll start with that first clue, then we'll investigate the crime scene itself, look at the opposing forces at play, uncover the absolute smoking gun, and then we'll deliver the final verdict. And stick around, because after that we'll look at the cold cases that are still keeping scientists up at night. Okay, let's get into it. Our investigation really kicks off at the exact moment everything changed. That old, comfortable idea of a calm, static, unchanging universe, it was about to be blown wide open. Here's a really crucial piece of the puzzle. The laws of gravity themselves. They basically demand that the universe has to be doing something. It's either got to be expanding or it's got to be contracting. The one thing it can't do is just sit still. For a long time, this was a massive headache for physicists. But then, back in the 1920s, an astronomer named Edwin Hubble made an incredible discovery. He saw that distant galaxies, all of them, are moving away from us. The universe wasn't just sitting there. It was getting bigger. This was the first real breakthrough in the case. And what's so wild about this is that even the great Albert Einstein just couldn't bring himself to accept a universe in motion. I mean, his own theory of general relativity actually predicted it, but he went and stuck in what he called a fudge factor, the cosmological constant, just to force his equations to show a static universe. So when Hubble came along and proved the expansion was real, Einstein famously said that fudge factor was the biggest blunder of his entire life. So now we have our first big clue. The universe is expanding. And this is where we can really start to think like detectives. If it's expanding now, that means we can play the cosmic movie in reverse. We can rewind everything back to a single point in time, the beginning. But how in the world do you figure out when it all started? Well, here's a fun way to think about it. Imagine the police show up and bust a huge party, and everybody scatters and leaves at the exact same time. You get home and you wonder, when did that actually happen? Well, if you know how far you drove and you know how fast you were going, you can easily calculate how long the trip took, right? Astronomers do the exact same thing, but with galaxies. They measure how far away a galaxy is and how fast it's moving away from us to figure out how long it's been traveling from that initial party. And that little calculation gives us something called the Hubble Time. It's basically just the flip side of the Hubble constant. That's the number that tells us how fast the universe is expanding. It's a really clever, straightforward way to get a first guess at the age of the universe, if you assume that the expansion has always been happening at the same speed. But of course, it's never that simple, is it? We now know that rate hasn't always been the same. So by factoring in how the expansion has actually changed over time, slowing down, speeding up, we've been able to get a much more accurate number. And our best evidence, our best calculation, tells us the crime scene is 13.8 billion years old. Okay, so we've got the age of the universe nailed down, but that was really just the start. The next part of this mystery involves a massive struggle, a kind of cosmic tug-of-war between two powerful forces, a battle that will decide the ultimate fate of, well, everything. For decades, the thinking was pretty simple. The universe is chock full of stuff, matter, and all that matter has gravity. So all that gravity should be pulling everything back together, acting like a giant brake on the expansion. So the big question for astronomers was, okay, how much is it slowing down? They went out to measure it, and they were expecting a pretty clear answer. They did not get the answer they were expecting. In 1998, the universe threw us the biggest plot twist imaginable. Two different teams were studying distant supernova, and they found that they were dimmer and therefore farther away than they should have been. There was only one possible explanation. The expansion of the universe isn't slowing down at all. It's speeding up. Something out there is hitting the gas pedal, and it's overpowering gravity.
And that discovery just revealed how truly weird our universe is. I mean, look at this. The stuff we know and understand, atoms, stars, planets, you, me, all of that makes up less than 5% of the cosmos. About 27% is this mysterious stuff called dark matter, which gives us some extra gravity. But then a staggering 68.5% is this dark energy. That's the name we've given to whatever is causing the expansion to accelerate. So we've solved one mystery, only to find out that 95% of our universe is a complete and total unknown.
So we have this incredible theory, a Big Bang followed by this runaway expansion. But every good detective knows you need a smoking gun, that one piece of irrefutable evidence that proves the event really happened. And for the Big Bang, that evidence is an actual echo from the dawn of time that we can still hear today.
See, in its very first moments, the universe was this unbelievably hot, dense soup of particles. And light was basically trapped inside, constantly bouncing off of loose electrons. It was like trying to see through the thickest fog imaginable. But then, after about 380,000 years, the universe cooled down just enough for those electrons to combine with nuclei and form the first real atoms. And just like that, the fog cleared. For the very first time, light could travel freely across the cosmos.
And that very first light, it's still traveling through the universe today. We call it the cosmic microwave background, or the CMB for short. Now, because the universe has expanded about 1,000 times since then, that initial brilliant flash of light has been stretched out all the way into the microwave part of the spectrum. When our telescopes look at the CMB, we are literally seeing the afterglow of creation. It is the perfect smoking gun.
Now here's where it gets really cool. The CMB isn't perfectly smooth. If you look closely, you can see it has these tiny little temperature changes, hot spots and cold spots. And the size of these spots gives us the final, ultimate clue about the overall shape and density of the universe. The measurements are absolutely conclusive. These spots are the exact size they should be if the universe is what we call geometrically flat. And what that means is it has just the right density to expand forever.
Okay, let's review the evidence. We have an expanding universe, we have a mysterious force, dark energy, that's making it accelerate, and we have a smoking gun, the CMB, that tells us the universe is flat. The case is pretty much closed. It's time to deliver the final verdict on the ultimate fate of our cosmos. For a long time, there were a few competing theories on the table. You could have a closed universe with so much gravity that it would all collapse back in on itself in a big crunch. Or you could have an open universe that would expand forever, but kind of slow down over time. Our reality, though, is shaped by dark energy and that flat geometry we talked about, and that specific combination points to only one possible outcome. So the verdict is in. The universe is going to expand forever. And because of dark energy, that expansion is only going to get faster and faster. Galaxies will fly farther and farther apart from each other until they literally disappear from view. The stars will all eventually burn out. The ultimate fate of our universe, the final chapter, is a cold, dark, and very lonely expanse. So, case closed, right? Well, not quite. Like in any great detective story, solving the main crime has left us with a handful of really fascinating new mysteries. These are the unsolved cases, the ones that are going to define the next generation of cosmology. I mean, think about it. We've built this amazing picture of our universe, but it's all resting on things we don't really understand. What actually is dark matter, the stuff that builds the scaffolding for galaxies? What in the world is dark energy, the thing that's pushing everything apart? Did the universe go through some kind of hyper-fast inflation in the first split second of its existence? And maybe the biggest question of all, why do the laws of physics seem so perfectly, so impossibly fine-tuned to allow for life to exist? And that leads us to one last really mind-bending thought. If the conditions in our universe seem just too perfect to be an accident, what if it's not the only one? What if our universe is just one bubble in a vast cosmic foam of other universes, a multiverse, where each one has slightly different rules? Maybe we're here asking these questions simply because this happens to be one of the universes where the conditions were, by pure chance, just right. Now that is a final mystery to think about.